Welcome back, students. In this lecture, we're going to talk in a bit more detail about the differences between Geospatial Data Science and GIS. When I began taking my first GIS courses as an undergraduate student in wildlife biology 30 years ago, there was not an emphasis on any specific type of GIS software. At that time, desktop computers were still quite expensive, especially one that would be powerful enough to run GIS software. To give you an idea, the first real GIS project I worked on ended abruptly when we determined that it would require 6 gigabytes of data and hard disk space. And hard disk space at the time cost $1,000 per gigabyte. And this project couldn't afford to pay even for the disk space, let alone the rest of the computer or the software. And just yesterday morning, I downloaded a set of point observations of bird species for all of Mexico, and I downloaded that file in about 25 minutes over the internet, and it was almost 9 gigabytes. And that didn't even make a dent in the storage capacity of my current computer, which has a couple terabytes of hard drive. So just downloading that data would have cost me $9,000 just to store the data 30 years ago. My university had a few workstations with ArcInfo, but the GIS lab was run like a consulting firm. If you wanted to use a workstation, you had to pay, and it wasn't cheap. So my first GIS courses were quite theoretical with very little in the way of hands-on experience. By the time I graduated with a minor in GIS and spatial analysis in 1994, I could discuss in detail how lines and polygons were modeled, how to compute an intersection or determine if a point was contained in a polygon, or compute a spatial correlation matrix by hand, and I could talk quite a bit about cartographic theory and concepts in geodesy as well. But if you sat me down in front of a computer with ArcInfo and asked me to do something, I wouldn't have had the slightest idea where to begin. And at the time, it was incredibly frustrating for me, but in hindsight, I think I benefited from getting the theory first. That all changed in late 1995 when Esri introduced ArcView 3.1. It was a relatively lightweight GIS system that ran in Microsoft Windows as well as on Mac and Unix, but it had its own graphical user interface that was much easier to learn than the command line driven ArcInfo. It had the ability to use shapefiles, which were a much simpler file format for vector data than the traditional ArcInfo coverage model. Despite its limitations, it was still a very useful program with a fair amount of analytical power. It even had its own programming language named Avenue. Best of all, it was freely available to students, most of whom had their own computers by that time, or at least had ready access to computers in university computer labs. As a result, most university GIS courses began migrating their curriculum to a more hands-on learning experience using ArcView, with less emphasis on theory and more emphasis on pushing the right buttons in canned software exercises. So you learned ArcView very well, but maybe not as much about geospatial theory. 5 years later, Esri released ArcGIS, which only ran on Microsoft computers. They ditched Avenue altogether and used Visual Basic as the programming language. And although student licenses were available, it became increasingly difficult to deal with the Esri licensing system. And as a result, university GIS programs were faced with a decision to either deal with the cost of upgrading the software and completely rewriting their curriculums, or teach their students in increasingly obsolete software. Several years later, Microsoft began phasing out Visual Basic, and Esri began migrating towards using Python as the scripting language for the GIS products. And a few years after that, they began phasing out ArcGIS in favor of ArcGIS Pro, which was able to take advantage of modern computer hardware with 64-bit multi-core processors and provided serious performance advantages, but required a complete rewrite from the ground up, and thus another entirely new interface and new Python API. And again, educators were required to completely rewrite their curriculums. Many universities began to see the weakness in focusing on software-specific courses and began looking into alternatives. At the same time, alternatives to commercial GIS software became increasingly available in the open source world. QGIS provided a desktop GIS experience on par with ArcGIS for many things, and in my opinion was superior for many applications. PostGIS provided geospatial analysis capabilities right in an enterprise level database that could handle amounts of data that would bring ArcGIS to its knees. GeoServer and other server technologies provided the ability to stream GIS data over the internet to be consumed by clients rather than storing that data on board in files. Web mapping applications provided interfaces for displaying and analyzing GIS data on web pages. Open source programming languages like Python and R soon had packages available for reading and analyzing GIS data from a large variety of sources. And most of these open source alternatives relied on a common set of technologies that were also open source and quickly became quite robust and efficient. As a result, there was a tendency to move away from canned software-specific GIS labs and return to a more theoretical and conceptual understanding. After all, a buffer or an intersection did the same thing, whether it was in ArcGIS, QGIS, a web application, in a spatially enabled database, or in a Python or R package. And so it's possible to do a lot of the GIS type things without even opening a desktop GIS program. And so even the term GIS began to fall out of favor because it was really associated with specific software. So while there were some very real changes going on behind the scenes to some extent, there was also just a cultural shift towards new buzzwords that sounded new and different. GIS programs became geospatial science programs or maybe geomatic programs, especially in Europe. This was partly because there was less reliance on GIS software, but the basic concepts were not much different. You had to understand how geospatial data is stored. You had to understand the basics of spatial operations. You had to understand the complexities of coordinate reference systems and map projections. And also at the same time, the field of statistics was undergoing a similar transformation. Most university statistics programs in the 90s and early 2000s relied on a commercial statistics program called SAS, which was the gold standard at the time. The problem for students was that once they left academia, SAS was rarer than hen's teeth and very difficult to get a license for on your own personal computer. And so it was hard to apply all that statistical knowledge that you just spent 4 years of your life learning. But open source solutions were becoming available in statistics as well. The R programming language began as a specialized language focused on working with data and performing statistical analysis. Because it was open source, new techniques were implemented in R long before they made their way into commercial statistical software, and students began demanding that universities teach R because they could run it freely on their own computers. So the term machine language began replacing statistics, especially for predictive statistical techniques that could be used to classify objects into groups or make model-based predictions. Although many of the methodologies, such as linear and logistic regression, were the same, the emphasis shifted from extracting information from existing data to using existing data to make predictions about the future or learning. And there was a lot of data available with the increasing power of computers and the ability to store and process increasing amounts of data. The internet and mobile devices allowed the collection of massive sets of data, which often was more than could be handled by a single computer and required special methods involving network clustered of computers for storing and processing all that data. And these specialized methods fell under the term big data. So a new field began to emerge known as data science, which is often described as an interdisciplinary field that integrates statistics and or machine learning with computer science, because especially when large amounts of data are concerned, it's useful to have a strong background in databases, programming, networking, parallel processing, etc. And once the analysis is complete, it's necessary to present the results to others. And so you need to have a solid background in computer visualizations to summarize your results in a manner that's clear and easy to understand. But after all is said and done, the primary goal remains the same, which is to extract usable information from raw data in order to make good decisions. And geospatial data is just data with a spatial component. After all, everything happens somewhere at some time, and so most data will have both a spatial and a temporal component. Not all, but most. So a question that I've seen asked several times recently has been, is spatial really special? Most of us with traditional training in GIS had thought that there was something very special about spatial data and spatial analysis, That required special software to work with and special training to understand. And certainly to work effectively with spatial data, you need to understand coordinate reference systems and all the issues around map projections and which one to use for a given situation. And you need to understand spatial data sources, what's available, where to get them, etc. And you need to understand spatial data formats, for instance, what's a shapefile, what's a geopackage, what's a file geodatabase, etc. And again, which is best for a given purpose. And spatial operations have a lot of additional operations that can be somewhat complex. Things like intersections, buffers, clipping, unions, etc. that must be understood very well in order to work effectively with geospatial data. And most of these things are covered quite well in university GIS programs, but it's often quite possible to go through an entire university GIS program without taking more than just minimal basic statistics course or two. So if you come through a data science program, you may not understand these things. You may have a very strong understanding of statistics. However, to analyze geospatial data as a data scientist, besides being well-grounded in statistics, you have to understand the spatial issues surrounding statistical analysis. In general, these result from the reality of spatial autocorrelation, which simply means that things that are located closer together tend to be more similar than things that are located further apart. As a result, if you collect data at specific points, the measurements are probably not completely independent, which violates the assumption in most statistical models, which assume that your samples are completely independent. And the result is a smaller effective sample size than your statistical model is estimating, because things that are located close together in space tend to be correlated. And if you don't take that into consideration, then the tendency is to underestimate the variance. And so statistical models have to compensate for that. And the methods to do that are not particularly straightforward, even among most statisticians. And finally, the visualization of your results will generally involve some type of a map, which is quite different than standard statistical plotting. Often it's necessary to plot out the residuals spatially as well in order to evaluate for spatial autocorrelation. So it's clear that in order to work effectively with spatial data, data scientists must add quite a bit to the toolkit, and so one could argue that spatial is special. On the other hand, spatial data is just really data. Raster data are just matrices. Vector data is just a combination of an attribute table plus an additional field that holds the coordinates in some kind of organized fashion that they can be used to create a line or a polygon. And this has been the case from the very beginning. Have you ever wondered where the info in ArcInfo came from? Info was an early database that Jack Dangerman co-opted to handle the attribute part of spatial data, while the Arc part related to the spatial extension that he added to it to create ArcInfo. Shapefiles were a combination of a DBase3 database table, that's the one with the DBF extension, combined with the associated coordinate information in binary format, and so that's the file with the SHP extension, along with some metadata, projection information, and index information, and each one of those took up a separate file. GeoPackages are a SQLite database that has tables containing coordinate information stored in a field in binary format. PostGIS is just an enterprise database that allows you to store geometry information in one field as binary data. GeoJSON combines attribute data with the geometry coordinates as JSON objects, etc. All these different file formats have the same basic structure. There's a table to hold your tabular attribute and also a list of coordinates that are linked to those tabular attributes to create the geometry. And PostGIS has over 1,000 functions for dealing with geospatial data. But they're simply custom database functions that are not conceptually different than any other database function. And since data scientists already understand databases very well, they are well poised to simply tack on some of the geospatial specialness to their existing skill sets, and to them, it may appear that spatial is not really that special and probably doesn't require specialized, complex, and expensive software. It's just another type of data to understand. And a data scientist would probably roll their eyes if you told them they needed to pay $4,000 for an ArcGIS license with spatial analysis extension in order to work with a raster when a raster is only a matrix and they're already familiar with NumPy or R packages that deal with matrices in much more powerful ways and that don't cost a penny because they're open source. So having said all that, what really is the difference between geospatial data science and GIS? Are you a data scientist or a GIS analyst? According to recent surveys, you would be paid quite a bit more if you claim to be a data scientist than you would as a GIS analyst, even if you were basically addressing the same question. And we've said several times that the approach is a little bit different, but I would argue that the biggest difference between them is the tool that they use. GIS analysts tend to rely on specialized GIS software that they are very good at. Desktop GIS software tends to be very good at cartography and very good if you prefer software with a graphical user interface where you can choose things from menus, etc. But they're not always great for working with large amounts of data, as data scientists sometimes do. In fact, ArcMap, the main commercial GIS software, is still a 32-bit program that mostly only uses one core, and thus only uses a fraction of the power available in most modern CPUs. The laptop that I'm using right now has 8 cores, and ArcMap will generally only use one of those. They also tend to have limits imposed by the GUI. For instance, ArcMap is Microsoft-based software and presumably uses the same grid widget as Excel does because it has a limit on the number of rows that's the same as an Excel worksheet, as I recently found, and that's just over 1 million rows. At least Excel told me that I had exceeded the capacity while ArcMap just continued like nothing happened with only 25% of my data, which in my opinion is a huge problem. If I hadn't caught it, I would have continued merrily along my way with only 1/4 of the data that I was intending to work with. Fortunately, in this case, I had no problem working with the data in a pandas data frame, which are limited only by memory, or storing them in a PostGIS table, which has a maximum size of 16 terabytes, which is incredibly large. And while you can certainly prepare your data for analysis in desktop GIS, most lack great tools for statistical analysis. It's also somewhat difficult to document your analysis with a GUI-based program. Most people will not be writing down every menu or button they click or all the parameters that they enter for a geoprocessing tool. That will kind of defeat the point of a GUI, which is to prevent you from having to type everything out. Although you can do some automation with graphical model builders, most people will not do so unless it's something that's repeated quite often. Data scientists, on the other hand, tend to be familiar with a set of open source tools that exist completely outside of specialized GIS software. They can store very large amounts of data in enterprise-level databases such as PostGIS that can be spread over clusters of servers and replicated automatically for robust performance. They also tend to be familiar with programming languages. In the case of data scientists, that language will probably be either R, which is a language specifically written for analyzing data, or Python, which is a more general-purpose language, but one that has a huge number of third-party packages available for working with data. And both of these languages can work with clusters of computers running in parallel to increase computational capacity if needed, and can also take full advantage of the multiple cores available in modern CPUs, and thus they'll use all the power available in your computer. And if that's not enough, again, you can create a cluster of multiple computers. If you write your code in a Jupyter notebook, it's quite easy to document every step, and if you ever need to defend your analysis for a scientific paper or use it in court, then it's all right there, and other people can see exactly what libraries you used, what methods you used, and the value of every single parameter that you used. On the downside, the data science approach is not great for cartography. Although you can certainly create some impressive maps, it's not necessarily straightforward. And there is a steep learning curve, although that's something that I'm hoping to address with this course to make things a little bit easier to understand for folks. The good thing is that you don't have to choose one or the other and commit to it. You can use whichever tool set is best for your needs, but only if you have some understanding of the advantages and disadvantages of each, And that's what we'll talk about in the next lecture, and we'll see you then.